Okay, so we're going to have the third lecture in the series of acids and bases. And again, I'm just setting my timer to make sure we don't go over. What we did last time was we defined an acid and a base. We looked at the factors affecting the strength of an acid. And we talked particularly about the importance of the stability of the conjugate base. What we want to do now is see what is the important, and in fact, yes, also we identified that we could rank acids based upon both the pKa's and the Ka values, and that we could, in the absence of those data, we could rank acids based upon those factors. So the factors again were the nature of the HA bond, both the length and the strength of the bond and the polarity. We looked and we saw how, if you're comparing periodic partners, that the issue was one of electronegativity. If you're comparing group partners, the issue is one of bond length or atomic size. The stability of the conjugate base, which was a factor of both inductive effects and resonance effects, which we call electronic effects. Also a factor of size and sort of electronegativity, and also hybridization state. And what we ended up doing last time is we were looking at a series of hydroxy acids. So we looked at cyclohexanol was one case. We looked at phenol as another case study. We looked at benzoic acid as a third case study. And we saw that of the three, the benzoic acid, so the Ka value, rises in this direction. And we explained that essentially by saying that the conjugate base of the species had significantly different stabilities. That the conjugate base in the alkoxide series was very unstable because the electron density was not spread, but in fact it was concentrated on the O. That the conjugate base from the phenol, the so-called phenoxide ion, was in fact a resonance form of a resonance hybrid of four resonance forms. Most of the negative charge was borne by the oxygen, but that the ortho and para carbons also bore some brunt of the electron density. But most of it was still on the carbon, still on the oxygen. Whereas in the case of the benzoic acid, the electron density was very evenly distributed between the two oxygens. So we had essentially what was a half minus on that O and a half minus on this O, versus something like 0.9 minus on the O, and then you share the remaining 0.1 minus over the three carbons. And we saw several things that, in fact, all things being equal, the more resonance forms you can draw, the more stable a species is. And that in general is true, except when you're comparing apples and oranges. So in the case of the carboxylate, I have two resonance forms that I can draw, but in both cases, the minus charges are on electronegative atoms. Not only that, but the two resonance forms are equivalent resonance forms. And there is a bonus stability that one encounters when the resonance forms are equivalent. Okay, and this actually comes out of the Schrodinger equation, that when you can draw equivalent resonance forms for two species, for a given species, that you get a bonus in stability. So in fact, the carboxylate is actually a fairly stable conjugate base, in which case it is a fairly unreactive conjugate base, and therefore if it's an unreactive conjugate base, it's a weak base, and in which case, therefore, the carboxylic acid is a modestly strong acid. The phenoxide, you can actually draw four resonance forms, but only in one of them is the negative charge actually borne on an electronegative atom. And so the stability of the phenoxide is somewhat lower than that in the case of the carboxylate. We did point out, however, that one, in fact, can mediate the stability of your phenoxide. So if I were to ask you to rank the following phenols in terms of their acidities, and let's say I gave you these phenols, so fluorine, 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 and by the way, well, let's not do that. well, I guess let's do that. The circle in the benzene ring really is the equivalent of these 3 pi bonds, and we will make a distinction about that again sometime soon. And let me compare these phenols. In fact, it would be wiser if I looked at this with these isomers. Okay, and let's look at these phenols. So the question is to compare the relative acidities of these phenols. Okay, so I'm looking at, let's call it phenol A, phenol B, phenol C, phenol D. And the question is, rank those in terms of the stabilities. Well, I'm going to take and again, so how would we approach this? And we ask ourselves, what factors affect the strength of an acid? And the answer is, well, the solvent, which I will assume will be exactly the same unless I'm told otherwise. So that would be a non-issue. 2 is the nature of the HA bond. And quite frankly, the acidic bond here is the OH bond. And I'm going to say that, to all intents and purposes, the OH bond is the same in A, B, C, and D. There may be subtle differences, but I can't imagine that there are going to be major differences that would cause a change in acidity. So the remaining factor then is the stability of A minus. So let's envision what the conjugate basis in each of these species will look like. And sure enough, if I draw the phenoxide, again, I can draw a resonance form. This is my phenoxide, in which the minus charge is on the oxygen, in which the minus charge can be on the ortho carbon, in which the minus charge can be on the para carbon, and again, in which the minus charge can be on the other ortho carbon. Hold on. There we go. Oh, son of a gun. So bang, bang, bang. Okay. So here, here, and then here, and here. I'm going to put this one here. Alright, so those are the 4 resonance forms that I can draw for that phenoxide. If I look at the conjugate base for this species, and I think you can get a sense of where this is going, it's going to look like this. And if you notice, and we sort of alluded to this at the end of the last lecture, I have placed electronegative atoms on the 2 ortho positions. And the consequence of that is, if I look at the hybrid for these 4 resonance forms, what it actually looks like is this. Right? What I would have done is I would have delocalized the minus charge over the oxygen, and specifically on the ortho and para carbons. Which means if I strategically place fluorine atoms, electron withdrawing groups, on the ortho and para carbons, what they will do in essence, and I'll just draw this resonance form then to sort of highlight the issue, is that they will stabilize the resonance hybrid by what essentially then is induction. So I'll have a delta minus charge here, and there'll be a fluorine. I'll have a delta minus charge here, and there'll be a fluorine. There'll be a delta minus here as well. And so the effect is that since these fluorines are electronegative, they will bleed significant electron density away from this carbon, in which case they will in turn accept more electron density from this O. So what was once a delta minus 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 on this oxygen, supported only by the poorly electronegative carbons, will now be changed into what I'm going to call a delta minus on this O, a delta minus here, delta minus here, and a small, well, maybe delta minus minus. And there'll be a small delta minus on this carbon. My point being that these fluorines will in essence bleed more electron density from this oxygen, so that the burden of the electron density is not supported by only one O. So I would have delocalized the charge over an O, 2 electronegative fluorines, and then a little bit on these 3 carbons. So if I've delocalized the electron density, if I've delocalized the charge, then the conjugate base is somewhat stable. If the conjugate base is stable, then it's relatively weak. It does not gobble up protons and go back into the acid, and therefore the acid is going to be relatively strong. My equilibrium will lie towards the side of the conjugate base. Now, there are also 2 fluorines on this compound. But if you look at the conjugate, at the resonance form, it should become immediately apparent that those fluorines are poorly positioned, that they're not where the hotbed of electron density is, they are away from it. And so yes, they will, by induction, also draw electron density from the carbons, but they are relying on 1-2 bond induction rather than 1 bond induction. And 1 bond induction is much more potent. Remember we said induction is very strong along the first bond, it is modest along the second, and then it's relatively weak along the third bond. So what we're saying then is that the stability provided by these two fluorines is certainly greater than it is in the case of the phenoxide, but it is not as great as is in the case of the phenoxide in species B. So far if I have a hierarchy, what I'm going to be suggesting then is, if I say in terms of my Ka values that here is A, I would certainly say that C is more acidic than A, but that B is more acidic than C. If I look at D, now I've got groups in the ortho and the para position. But those groups are in fact nitro groups. And why is it important? The answer is, if I draw the nitro species out, there are two things that become immediately obvious about the nitro. And those two things are, the N of the nitro actually has a formal positive charge. Now remember, N is the world's third most electronegative element. That is when the N is simply sp3 hybridized. If I make the N sp2 hybridized, as it is here, and I give it a positive charge, I would have souped up the electronegativity of that N, which means its ability to bleed electron density towards itself is going to be huge. Add to the fact, and this is what I'm going to do now, I'm just going to draw one of the resonance forms because it will, I think, make the point. If I draw the resonance form here, what you will see is that placing that nitro group on the ortho position, and then as it turns out the para as well, in addition to the inductive stabilization that nitro group affords, there is also the fact that I've now placed a minus charge 1 bond away from a double bond. So I can draw a resonance form that involves the nitro. So not only do I have inductive stabilization by the N, but I also have resonance stabilization by the N, by the nitro group. And that resonance stabilization deposits the minus charge on an atom that is actually an electronegative atom. It's an atom of oxygen. So what I'm actually getting then is not just inductive stabilization, but really quite effective resonance stabilization in the nitro phenoxide. And of course, if I put 2 nitro groups on, there's massive amounts of stabilization. So compound D is actually a very strong acid. In fact, it turns out that if you actually look at a series of phenols, that if you look at phenol itself is actually only a modest acid. But if you place the nitro group on the phenol, so you look at O-nitrophenol, this is O, or ortho-nitrophenol. O-nitrophenol obviously then is a stronger acid than phenol. If I look at the phenol, where there is a nitro group in the ortho and in a para position, you might expect this to be an even stronger acid than this one. So if I call this 2,4-dinitrophenol, that's even more acidic. And this particular compound, which is 2,4,6-trinitrophenol, 2,4,6-trinitrophenol, where I have placed powerful electron drawing nitro groups on both ortho and para positions, this is referred to as picric acid. Picric acid is an extremely strong acid. I mean, it's as strong as a mineral acid. It's about as strong as, for example, HCl. And it really is quite astounding how the placement of groups that are very strongly electron withdrawing, because they do it both by induction and resonance, can make a massive difference in the Kas of these four compounds. I mean, the Kas are changing by orders of magnitude as I go from the phenol to the nitrophenol to the dinitro to the picric acid. Now, there's a little interesting issue that comes about as a consequence of the change from cyclohexanol to, well, let's not do it that way, from cyclohexanol to phenols to carboxylic acids. So I'm going to say in general, when I look at alcohols and phenols, so pH is a shorthand way of writing phenyl. So this is called a phenyl group, so I can write phenol as PHOH. And then, for example, a carboxylic acid, right? All of these three compounds are functionally acidic. And it turns out that in general, if I don't put substituents on them, right? Because, for example, a phenol is in general a weaker acid than a carboxylic acid. But if I take O-nitrophenol, this is stronger than a carboxylic acid. If I take the trinitrophenol, it's so much stronger than a carboxylic acid that it's as strong as a mineral acid. It's strong as nitric acid or as HCl. So just the placement of one nitro group lifts the phenol's acidity above that of a carboxylic acid. Okay? But if I look at unsubstituted alcohols and phenols and carboxylic acids, it turns out that their responses to their acidities may be demonstrated quite nicely by their behaviors with three different sodium species. So with alcohols, phenols, and carboxylic acids, if I place them in contact with sodium, I'm going to get a very violent reaction. And the idea is that any compound, I'm going to say X with a hydroxy group, will react with sodium to give rise to the sodium XO minus and hydrogen gas. Okay, so let me write that so there's a bit more room for you to see it. So any species XO minus, XOH will react with sodium to give NaOX plus, in this case, half a mole of hydrogen gas. So all of these compounds will violently evolve hydrogen gas with sodium. On the other hand, if, for example, I take these compounds and I treat them with aqueous sodium hydroxide, only the phenol and the carboxylic acid will actually react with sodium hydroxide. Now let's understand what's happening here. If I take, for example, an alcohol that is not soluble in water, so this would have to be an alcohol that has more than 5 carbons, for example. So if I took cyclohexanol, or if I took decanol or octanol, those are not miscible in water. Okay. If I treat them with aqueous sodium hydroxide, they will not dissolve in water either. Now, this is a silly experiment to run on ethanol, because ethanol will dissolve in water, which means it will dissolve in aqueous sodium hydroxide. So the test is useless on alcohols that are already water soluble. But if I have an alcohol which is not water soluble, and I treat it with aqueous sodium hydroxide, it will also not dissolve in water. On the other hand, phenols, which are not water soluble, right? Phenols only have one OH for 6 carbons, so they're not water soluble. If I take a phenol and I treat it with sodium hydroxide, this is a simple acid-base reaction to give the sodium phenoxide and water. So acid plus base gives rise to the salt, Na plus phenoxide plus water. I'll get very much the same reaction with a carboxylic acid. So carboxylic acids, excuse me, react with sodium hydroxide, and they will give rise to the sodium carboxylate, right, minus plus. There will be evolution of, and there will be formation of water, H2O. So acid plus base gives rise to the salts and water only. So carboxylic acids that are not water soluble right? For example, pentanoic acid, hexanoic acid, and so on, will dissolve in aqueous sodium hydroxide. So if I have a compound that I believe has a hydroxy group, because I may have run an NMR or an IR, and I know it has a hydroxy group, and this compound does not dissolve in water, if I treat it with aqueous sodium hydroxide and it does not dissolve, then I can say that compound is an alcohol. If I have an organic compound that I know has an OH group, and it's not water soluble, but I treat it with aqueous sodium hydroxide and it dissolves in water, then that compound may either be a phenol or a carboxylic acid. Well, how would I distinguish between phenols and carboxylic acids? And the answer is in terms of the reaction with aqueous sodium bicarbonate. So sodium bicarbonate will react with carboxylic acids, not with phenols. And in that reaction, I'm just going to write the bicarbonate as HCO3-, because the sodium, of course, is just a spectator ion. And what I would get would be the carboxylate plus carbon dioxide plus water. So if I treat the carboxylic acid with aqueous sodium bicarbonate, I will get effervescence, right? I'll get effervescence, carbon dioxide will be released, and I'll get my salts and water. So I can use sodium hydroxide and sodium bicarbonate to distinguish between the various acidic hydroxy compounds. So if I get a compound which dissolves in bicarbonate but not in aqueous sodium hydroxide, then that compound would have to be a carboxylic acid. Now, there's a caveat. Remember, we are talking about unsubstituted phenols. All bets are off if I start to place nitro groups, especially strategically, on the phenol. So if I had O-nitrophenol as my candidate, the O-nitrophenol would dissolve in both sodium hydroxide and sodium bicarbonate with effervescence. Because as I said, the O-nitrophenol is even more acidic than a carboxylic acid. All right, so here's the question. So we can rank acids in terms of their relative strengths. What do we do with that information? And it comes down to a very important feature of organic chemistry, and that is in terms of deciding the position of equilibrium of an acid-base reaction, right? In other words, what we want to do is to determine, right, the outcome of an acid-base reaction. So I'm going to give you a really silly example, right? This is one that we have a background for because we just discussed it, and we would have seen this in Gen Chem or even in high school. Suppose you were an alien coming to the planet and you wanted to find out what happened when I treated water, HOH, better yet, H3O+, you wanted to find out what happened when I treated H3O+ with OH-. Right, that was your question. What happens when I treat H3O+ with OH-? Now, I know this is an acid-base phenomenon, okay? And in fact, I'm going to change this example a little bit. Just bear with me a second. Let's make it, what would happen if I treated HCl with OH-? That's a little easier to do. Well, I'm going to say, look, this is a question of an acid-base reaction, right? But an acid is a proton donor. If I look at hydroxide, I'm saying, well, look, hydroxide has a proton on it, and certainly the HCl has lone pairs on it, right? So technically then the HCl is an electron pair donor. So I can easily see a case where the HCl can act as a base, right? Because it has lone pairs of electrons it can accept, that can donate electron density, and that's my definition of a base. I can easily see the hydroxide acting as an acid because the hydroxide has protons on it, and so it can function as a proton donor. And I know that things like oxides, right, exist. So maybe one option is the HCl reacts with the hydroxide and gives rise to a product. Now I'm going to redraw the hydroxide slightly just to give you a sense of what this might look like from a curved arrow perspective. So here's my oxide. So what would happen is the HCl would use a lone pair of electrons, form a new ClH bond, and I would break the bond between H and O minus. What would that give me? Well, I will have HClH. I'll have two lone pairs left on the Cl and a positive charge. Now, understand, I can argue that very easily if I were to look at the complete Lewis structures, okay? Or I can simply say, look, you know, the Cl was neutral when it had a lone pair. In forming the bond to the H, it's fundamentally given up an electron to the H, and therefore it's going to have a positive charge. Or I can say the electrons that belong to the chlorine are 1, 2, 3, 4, 5, 6. It's a group 7 element, hence a positive charge. And I can easily argue that what I've done here is I've taken the two electrons, one of which belong to the O, one of which belongs to the H, and I've given them both to the O. So the O must acquire a 2- charge. So one option is HCl acts as a base, accepts a proton, or if you will, donates an electron pair to hydroxide, and gives rise to H2Cl plus and O2 minus. In which case, the species formed by the base getting a proton will be the conjugate acid, and the species formed by the acid losing a proton would be the conjugate base. I could define them another way. I can say, look, if the reaction went backwards, what role does oxide play? And the answer is oxide would be the electron pair donor, or it would be the proton acceptor. Therefore, it is the base. What role would H2Cl plus play? It would be the proton donor, or the electron pair acceptor, in which case it's the acid. So certainly one option is HCl acts as the base, and we get this reaction. Well, there's another option, and the other option is, well, maybe the hydroxide, which actually has lone pairs and a negative charge to boot, might actually function as the base in this reaction. Right? In other words, the HCl acts as the acid, the hydroxide acts as the base, which is another alternative, and what we get would be this reaction. So we would get Cl minus, and we would get H2O. In which case, I would define the species formed by the acid losing a proton as a conjugate base. And I would define the species forming the base accepts a proton as the conjugate acid. Now, both of these reactions are from a philosophical perspective possible, right? This can certainly act as an acid because it has protons, and it is attached to an electronegative atom, although that electronegativity is compromised by the minus charge. This can certainly act as a base because it has lone pairs. Or it can act as an acid because it has H-bound electronegative atom, and this can act as a base because it certainly has lone pairs. And the question is, which one happens? So how do we answer that? And the answer is as follows. What I need to do is ask the question, if I compare my bases, HCl versus oxide, or I compare my acids, hydroxide versus H2Cl plus, where is the strong species? In other words, is HCl a stronger or weaker base than oxide? Or is hydroxide a stronger or weaker acid than H2Cl plus? So let's ask both questions. So which is the stronger base, HCl or O2 minus? Well, let's see. HCl has 3 lone pairs of electrons on a chlorine. Oxygen has 4 lone pairs of electrons on an oxygen, and there's a 2 minus charge. So what's the difference? Cl is a big atom. So in fact, I'm gonna redraw this really kind of badly. This is the chlorine atom, and it's got 3 lone pairs on it. Whereas the oxide, and this is really a bit too extreme, because the oxide is not that much smaller than a chloride. Let's make this the oxide. Oxide has 4 lone pairs and the 2 minus charge. Now, what is a base? A base is an electron pair donor. Which species will be more desperate to give up an electron pair, to donate an electron pair? And the answer is the one where the electron pair is less comfortable. What would make it uncomfortable? And the answer is repulsion. So in the large Cl, I have 3 pairs of electrons, right? Well, those electron pairs, oh, for God's sake, those electron pairs are distributed around the large chlorine. So the electron pair distance is actually relatively large, right? So the force of repulsion, which depends upon how close my electrons are to each other, is going to be relatively small because the chlorine atoms are relatively big. So the electron pair distance is long, and therefore the repulsion is small. Not to mention the fact that the chlorine here is neutral. So certainly it can donate an electron pair, but it's not desperate to do so because electron pairs are not that uncomfortable. If I look at the oxide, not only do I have 4 electron pairs around a smaller O, so clearly the electron pair distance is much shorter, in which case R is a smaller number and the force repulsion is greater, the instability is greater, right? The base is therefore more reactive and therefore stronger. But there's a 2 minus charge, for God's sake. So it would behoove this species to give up electron pairs, right? Because if I gave up the electron pairs, I decrease the inter-electronic repulsion, and I decrease the charge, negative charge in the O. So of the two, the oxide is a much stronger base than the HCl. Well, what does that mean? When we do a reaction, we tend to fall downhill, right? You know, rain falls down, a ball rolls down a hill, a stretch spring relaxes. Reactions tend to go from high energy states to low energy states. When we say a species is reactive, we mean it's a high energy entity. When we say a species is unreactive or stable, we mean it's a low energy entity. So the whole question of acid-base reactivity, or acid-base reaction, is going from a reactive species, or a strong base, a strong acid, to a weak one. When we say an acid-base reaction goes and the equilibrium value is large, it means we're going from a strong or reactive acid or base into a weak or poorly reactive acid or base. In other words, the strong gives the weak. A strong acid would make a weak acid. And why is that? Because I'm going downhill. A strong base will give a weak base. And why is that? Because I'm going downhill. What that also means is, if the strong gives the weak is the spontaneous path for a reaction, then the weaker base will never generate the strong one. Therefore, this reaction cannot go as written because it's suggesting that the weaker base, HCl, spontaneously gives rise to the stronger base, which is oxide. That cannot happen. Now, because it cannot happen, it must mean that hydroxide, in fact, must be a weaker acid than H2Cl+. Now, that must be true, so that the two weaks have to be on the same side. The two strongs must be on the same side. But instead of arguing HCl as a base versus oxide as a base, I could have just as easily argued hydroxide as an acid, right, versus HCl as an acid. Okay? So here's how we're going to do that argument. Here's my chlorine. That's not quite... So here's how we're going to do the argument. Here is my hydrogen. Here is my oxygen. Right? This is hydroxide. Here is my hydrogen. Here is my chlorine. Oh, good Lord. Here is my chlorine. Well, you get the point. Right? So here's the chlorine. I'm sorry. Yeah, I'm going to go back to my first diagram. So here's my H, here's my O, all right? This is hydroxide. Here is my H2Cl plus. I'll just do it this way. The bottom line is that chlorine is a bigger atom than oxygen. Therefore, the HCl bond is going to be longer than the HO bond. So if I'm comparing hydroxide as an acid versus H2Cl plus as an acid, what do I look at? The answer is I'm comparing O versus Cl. The chlorine is a bigger atom, so the bond is longer, right? And if the bond is longer, the bond is weaker. And as a result, the acid should be stronger because the weaker bond will break more completely. That's issue number one. Issue number two is that if I look at the polarity of the bond, yes, O is electronegative. And it will certainly bleed some electron density from the H, but its ability to draw electrons from the H is compromised by the fact that the O is already negative. So let's say it's going to bleed that much and there'll be a delta plus charge on my O. Chlorine has the same electronegativity as O. O minus has a smaller electronegativity than O, and Cl plus has an even greater electronegativity than O. In other words, Cl plus is now much more electronegative than O minus. So not only is the HCl bond longer and weaker than the HO bond, but for heaven's sake, the bond is also more polar. The dipole in this H is going to be huge. So when we consider the nature of the HA bond, what are we asking? We're asking how long is the bond, because that speaks to the strength of the bond. And we're asking how polar is the bond. So if the bond is longer and weaker, and the H is more protonic, then hands down, H2Cl plus must be a much stronger acid than OH minus. And if that's true, this reaction cannot occur as written, because it would mean the weaker acid gives rise to the stronger acid, and the weak cannot give the strong. So I can say then that this reaction does not go, that hydroxide does not function as an acid. Okay? Now, understand two things, and this is where we end this lecture. Understand two things. One, we never once asked the question, is HCl a stronger acid than hydroxide? Or is hydroxide a stronger base than HCl? That is not the question. Acid-base phenomena are equilibrium phenomena. And so what I have to do, if I have a seesaw, and I have an object here and an object here, I'm not going to ask anything about this object and this side of the seesaw. I'm interested in this object relative to its counterpart on the other side. That's how I know where the equilibrium lies. So I'm not concerned about comparing HCl to hydroxide. That's irrelevant. I am concerned with comparing HCl as a base against the conjugate base. I am concerned with comparing hydroxide as an acid against the conjugate acid. So I am looking at equilibrium across the equation. That's issue one. Issue two is not because the top reaction does not go, does it mean by default that the bottom reaction does go. Because it is perfectly legal to mix A and B and have nothing happen. Chemistry does not occur because you mix stuff. Chemistry occurs for a reason. And as far as acid-base reactions go, the reason is that the strong acid gives rise to the weak, and the strong base gives rise to the weak. So does the second reaction go? Does HCl react with hydroxide to give Cl minus and water? Well, how do I answer that? I answer it by asking another question. And the question will be, which species, right, HCl or water is the stronger acid, right? I compare acid to acid. Which species, hydroxide or chloride, is the stronger base? Well, let's see. All right, let's see. Oh, come on. So I'm comparing hydroxide, right, as a base against chloride. So here is hydroxide, HO minus, and Cl minus. Right? Now, they both have a 1 minus charge, so that's a wash. I have 3 lone pairs over a small surface area, 4 lone pairs over a larger surface area. So the repulsion between these lone pairs is much less than repulsion between those lone pairs. So the electron pressure on hydroxide is greater. Of the two, hydroxide therefore must be the one that's more desperate to get rid of electron density. Vis-a-vis, it's the stronger base. If hydroxide is a stronger base than chloride, then the reaction will go, because the strong base gives rise to the weak base. So if hydroxide is a stronger base than chloride, it must mean that HCl is a stronger acid than water.
Auto shutdown sequence in progress. Primary.
Yeah, so it's time to stop. Right? It must mean that HCl is a stronger acid than water. Let's make sure that's true. So I'm comparing water, HOH, against HCl. So in water, I have H bound to O, and O is as electronegative as Cl, but the HO bond is shorter. Right? So the two bonds have the same polarity, but the HO bond is shorter, stronger, more difficult to break, and doesn't break quite as completely as a longer, weaker HCl bond. Therefore, HCl is a stronger acid than water, in which case, right, HCl is a stronger acid than water, so the strong gives weak, and the reaction goes as written. So that's how I determine the outcome of an acid-base reaction. I identify the base, acid-base, identify the base conjugate base pair. I identify the acid conjugate acid pair, and I ask, and I reason, where is the stronger species? Now, I do not have to do both. In other words, if I can prove that hydroxide is a stronger base than chloride, I do not have to also prove that HCl is a stronger acid than water. I need prove only one, right? Because if I say this is stronger than that, it must mean this is stronger than that. I don't have to do them both. Okay? So here's what I want you guys to do for me as an exercise. What I want you to do is to take your textbook, look at the table. There's a table of acids and bases. And it'll rank about 15 or 20 acids in terms of Ka values. And on the other side of the table, it'll rank them in terms of, rank the conjugate bases. I want you to, at random, pick pairs of acids and bases. And I want you to reason, I'd like you to do the exercise maybe 7 or 8 times. Show that one acid, explain to yourself why one acid is stronger than the other. So just pick any pair of acids and base of acids and compare them and show that acid A is stronger than acid B. Do the same thing for the bases. Pick 5 pairs of acids and then 5 pairs of bases and prove to yourself why one acid is stronger than the other. Okay? So we'll continue this exercise in the next lecture. We'll actually do one more because these are all sort of 35-minute bits. And we'll continue from there next time.